Okay, well, hello everybody. It's just about 8 o'clock, so I am monitoring the chat feed. Again, this is my first time doing this, so if you guys could just let me know if you can hear me okay and if it's coming through. Okay, so let's go ahead and get started. So again, you guys can find all of the problems online. Hopefully you can see those on the Google Classroom. If you can't find that PDF or you don't like it, you can just search 2012 AP Stat multiple choice. And we're going to bounce around a little bit. I've decided to just skip a couple so we can try to get through as many as possible. And if you guys want any more clarification, I do think there's a little bit of a delay. So you just want to make sure that you post something to the classroom and I can go back and answer your question. So thank you guys for being here, and we'll go ahead and get started. So the first one, it says, of the following dot plots, which represents a set of data that has the greatest standard deviation? So let's just remember our formula for standard deviation, which I already messed up writing, the very first thing. But basically what it says is each value, we take away the mean, we square it, because remember, if we just look at the distances away from the mean, they'd always had to give 0. We add up all those, and we divide by n minus 1, which was kind of weird. But remember, the whole point was that Sx was a biased estimator for sigma x. So we had to divide by n minus 1 to make sure that that thing worked out. Now remember, biased deals with sampling distributions. It meant that it was it was underestimating what sigma was supposed to be. So we changed it dividing by n minus 1. At any rate, that's just review. When we talk about standard deviation, we're just talking about distance from the mean. Okay, average distance from the mean. So we look at these dot plots and we say, okay, which of these has the most values furthest away from the mean? Now the most furthest away. So if we look at all of these, we can see that A has a lot of variability, for sure. But if we look, these values here in the beginning are pretty close to the mean. They would not have large deviations. But then take a look at B. The mean is obviously in the middle because this data would be symmetric. And what do we notice about all these values? They're all really far away. They would give you large deviations. So that would be the largest one. So there we go. Number 1 is letter B. Okay. Number 2, go into this. So this is a good box plot review. So a random sample of 374 pennies were collected and the age of each penny was determined. According to the box plot, what is the IQR? IQR. So this is always good. Now remember, IQR is a measure of spread. And it's Q3 minus Q1. So what it does is it tells us about the middle 50%. Okay, so remember Q3 matches up with our third quartile or the 75th percentile. Q1 is the 25th percentile. And when we see a box plot, that ties in directly with our 5-number summary. So let's just, again, I'm trying to review as many topics here as possible. So a 5-number summary are the 5 values that you usually see in the box plot. So we have a min, our Q1, the median, the Q3, and then we have our maximum. And so that's our 5-number summary. So it goes min, Q1, median, Q3, and the max. Okay, so we can see how those all work out. So that's what we have here. So now in this one we need to determine the IQR. And the IQR in this scenario, if we kind of look over and we just have to kind of use our best judgment, looks like maybe it's 18. Looks like Q1 is probably going to be about 7 or 8. So it looks like to me the closest one that we're going to have, if we subtract those, actually no, this is probably looking more like 4, isn't it? So it looks like 18 minus 4, so it looks like the closest one to me is going to be about 16, I think. So we'll go with that one with 16. It's a little bit tough. Now one thing to review is, what do you notice about that point? That's an outlier. So let's just remember our outlier formulas, because these are just little things that we can put down on flashcards to remember. So an outlier, remember, is any value that is more than 1.5 times the IQR away from the quartiles. Now never use the median, so it'd be Q3 plus 1.5 times the IQR. Or it'd be Q1 minus 1.5 times the IQR. And again, these give us our fences. It's any value outside of this. So any value outside of these fences. And then remember, our box plot connects to the next value that's inside of that. So we wouldn't ever connect to the fences unless that happened to be a value. So if that wasn't a value, then we find the next value that is. So in this scenario, we can see how that works out. Now visually, one trick that you can do is put your fingers on Q3 and Q1 and find that distance, extend it by 1/2, and then move it away. And we can see that that fence is somewhere around there, so therefore we can see the outlier. It's just a little trick visually to see it sometimes. Okay, moving on. Number 3 I'm going to skip, but if you want to go back and take a look at it, the answer is letter B. It's skewed to the left. That's a nice easy one. Remember that it's always whichever way that the tail points, if you drew that little monster in, right? And you always remember which way the tail points, tells you the shape. Remember, always be careful to say anything about normal distribution. Chi-square does not have its own distribution. Uniform means that it would just be the same all the way across. Okay, so just a couple little things to talk about, even though I said I wasn't going to review. Number 4, I'm also going to skip this one. That one is going to be letter E. So I'll let you guys just take a look at that one later on. Number 5. Okay, so here we go. So we still get to talk about a histogram. Now remember, histograms display quantitative data. So they're best for quantitative data. Remember, quantitative data is anything that you can take the average of. So data that you could average. And a lot of times it's numerical data, but we try not to just restrict it to that, because some numerical values we couldn't average, or the average wouldn't make sense. Remember, with Histograms, we create bins. So this interval would be from 0, probably inclusive on 0, to 5. And then the next one would go from 5 to 10. And we count how many values fall into each of these. Now, histograms, it's always important that they touch unless you had a gap that was there. So this one asks us which of the following could be the median wait times. These are always great questions. And the thing that you want to use here is we need to use our formula to find the median. So to find the median, there's that simple formula. You take the number of items that you have, add 1, and divide by 2. Now remember, from the beginning of the year, so this only tells us the location. So that's very important. So they gave us a huge trick, or a huge tip here. They told us there was 175 patients. So because of that, I know what n is. So therefore the location would be at 175 plus 1 divided by 2, which is 176 divided by 2, which I think is 88. I don't have anybody to give me feedback, but I'll go with it. So that says that the median is at the 88th value. Now that would be the same as the 88th value from the bottom or the 88th from the top, but guess what? It's way easier to count from the bottom. We notice that there's 80 values that fall in here. So person 0 through person 80 fall here. Then in the next one would be person 81, and it looks like 50, so we'll say 81 through 130. That's the 81st person to the 130th person. So therefore, we were looking for where's the 88th person falls, so it must be between this bar right here. So it has to be a score between 5 and 10. The only answer that matches up with that would be letter B. Now just a quick review. If I wanted to find the Q1, I would ignore the median. Remember, we never count the median, so there'd be 87 values underneath it. And we would add 1 and divide by 2. And that tells us that actually both quartiles essentially would fall. 88 would be the 44th value in. Okay. Now they're not asking us for this, but the 44th value would obviously fall in between 0 and 5. Or I could count 44 from the top. And again, this would be kind of tough, but 5, 10, I don't know, maybe 20. And then we could see that the 20 through 40 would probably be in here, so Q3 would probably fall somewhere here. But that's a tough one. Okay, moving on. Number 6 I'm going to skip just because of the problem. It would take us a little while to do it. But if you want to take a look back at that, number 6 is letter A. And remember, you guys can always go back and pause this or slow it down if I'm talking too fast. I'm sorry. Number 7. All right, good little review question. Just talking about z-scores here. So always a great skill to have. Remember the z-score, our formula, is the value minus the mean divided by the standard deviation. Now in this scenario we're just talking about one bear. So that's why it's this formula. We've been focusing a lot on sampling distributions, which is when we're talking about a group of bears. And remember that a z-score is simply the number of standard deviations a value falls from the mean. That's it. If it's at the mean, it would be 0. If it's above the mean, it would be positive. Below the mean, it would be negative. So in this scenario, they tell us that the first one, and key things when we read this, underline normal with a mean of 500 and a standard deviation of 50. So that's a male. It's normal with a mean of 500 and a standard deviation of 50. Females, again, are normal with a mean of 300 and a standard deviation of 40. So what would be the weight of a female grizzly bear with the same z-score as a male that's 530? Okay, so what we'll do is we'll find the first z-score for the male. So Zm, so it would be 530 minus 500 divided by 50. That's going to give me a z-score of 30 out of 50, which would be 0.6. So that says the male bear is 0.6 standard deviations above the mean. So now we need to do the same thing for the female bear, except we just have to work off of the z-score. So 0.6 equals x, we don't know her weight, minus 300 divided by 40, and we'll cross multiply from here. That would leave me with 24 equals x minus 300, and then it would be 324. And there we go. Now with test-taking strategies, we could always just find the z-scores of all the female ones if we totally got stuck and didn't know how to solve that. So again, don't be afraid to use your strategies for this test. You can find all those z-scores. You're going to have time. 90 minutes for all these multiple choice is plenty of time. Okay, number 8. This is a great one that I wanted to make sure that we took a look at. So this is a probability distribution. Now remember, key things with probability distributions, we have all of the outcomes here and the probabilities. Now to be a proper probability distribution, all the probabilities must add to give 1. Okay, so that's important. And they tell us the expected value of the probability distribution is 19.25. Let's just remember, expected value is the same thing as the mean of the distribution. And this is right on your formula sheet. This says we take the summation of all the values of x times the probabilities. Okay, so just for instance, in this scenario, we do 10 times 0.15 plus 15 times 0.25 plus 20 times 0.25 plus 30 times 0.05. Not that I saved much work by skipping one. And we come up with 19.25. They gave that to us. I know you don't have to do that. Again, we're reviewing concepts here. The standard deviation of x, which again is on your formula sheet, is basically the same one as before. We take each value, subtract the mean, square it, otherwise they would add up to give 0. That's the point of the mean. It balances the distances. And then the only difference from before is we multiply by the probability. So just to plug in one or two, so we do 10 minus 19.25 squared times 0.15 plus 15 minus 19.25 squared times 0.25 plus go to the last one, 30 minus 19.25 squared times 0.05. And there we go. And that adds up to give us our standard deviation of 5.76. Now that wasn't even part of this question, but again, we're trying to review. So what is the question? They tell us that the profit goes by this formula right here. Y is 75x minus 100. Now let's just remember, so what this basically says, and if you guys totally get stuck on this, right, you could make a new variable up here called y and do 75 times 10, or 75 times the value and subtract 100. So this would be 650. And the next one, I don't know, it would be 75 times 15. 75 times 15 minus 100, so it would be 1025. So if I totally got stuck, I could do this. I could change all these values and then plug this into one list, the probability into the second list, and run my 1-var stats. And that would be totally fine. You'd get the same answer. But what they want us to use is they want us to use our transformation rule. So basically the question is, does multiplication affect the spread, and does subtraction affect the spread? So the standard deviation of y, remember how this works out. We can do this one of two ways. We know that multiplication affects the spread, but addition and subtraction doesn't. So I can either do one of two things. I can take 75 and multiply by the standard deviation of x, which is totally cool, which was 5.76. Okay, and if I work that out, that's going to leave me with 432. Now in class, we focus more on variances a lot, but it works out to be the same. Remember, for variance, we would do 75 squared times the variance of x. It's a good rule for when we combine random variables, so 75 squared times 5.76 squared. And then we square root to get back to standard deviation, so which would obviously give you the same thing. Okay, so there we go. 2 ways to do it. Again, this way is a lot easier, right? But this way is our better rule for variances. Now, just to remember, what if I needed the mean of y? Well, so again, the question is, does multiplication affect the mean? Yes. Does subtraction affect the mean? Yes. Remember, whatever you do to the data, you do to the means. So we would do 75 times the mean of x minus 100. And I don't know what that is, but it would be 75 times 19.25 minus 100. And there we go. So again, our linear transformation rules, Whatever we do to the data, we do to the mean. Spread is only affected by multiplication. And obviously division as well. And now this is just talking about the one random variable, so make sure you understand that. This isn't talking about combining random variables, so we're just talking about one variable, which was x. Okay, moving on. All right, number 9. So based on a survey of 900 people, so we should always kind of jot that down, n is 900, a journalist reports that 60% of adults in the United States are in favor of increasing the minimum hourly wage. If the reported percent has a margin of error of 2.7%, what is the closest to the level of confidence? So we're talking about a confidence interval. So we need to think here, what is our formula for a confidence interval? Well, we first have to ask ourselves, do we have categorical data or quantitative data? And in this scenario, they said that people either would be in favor or not in favor, which would be categorical data. How many samples do I have? 1 sample. So this tells me that we will be doing a 1 proportion z interval. So let's remember our formula here. P hat plus or minus z star times the square root of p hat, 1 minus p hat, all over n. Remember, we use p hat because we don't know what pi is, right? And they gave us p hat in the problem. And in this scenario, they gave us the margin of error. So let's remember, with any confidence interval, we always have our estimate. That's our best guess for the parameter, plus or minus the margin of error. So there's my margin of error. And they tell us that they want that to be within 0.027. So if you understand that, and we're looking for confidence level, basically my question is, what is z star? And then I can use my formula sheet to backtrack and figure out what z star would match up with that. Okay, so let's go ahead and do this. So I only care about this chunk. Okay, so 0.027 equals z star, that's what I'm looking for. And they gave us p hat, and they gave us n as 900. Okay? Now if I got here, and I'm not good at math, couldn't I go look up these different z stars to help figure out what my confidence would be? Now remember, you can find all of those z stars on your formula sheet, which is your t distribution table. So remember, z is all the way at the bottom, so here's your t table. All the way at the bottom gives you a different z stars. So we know 95 is 1.96, 90 is 1.645. So we can plug these in to find which one gives me 0.027. But I think we can also do the math. So I'm going to do that first. So the square root of 0.6 times 0.4 divided by 900. Okay, so 0.027 equals z star times 0.016. Now I'm rounding here, but I would never round in my calculator. So 0.027 divided by that answer, and I get 1.65. And if I go look at my t-chart, and I know this one, we can see which one gives me 1.65. Bottom row t star has to be 90% confidence. And there we go. All right, doing good. All right, let's take a look at the next one. So number 10. So number 10 is talking about an experiment. Okay, I'm going to make it a lot easier for us. The answer here is letter D, so let's just talk about why. So basically it says, can we provide an explanation for our conclusion? So they found a significant difference, and they randomly assigned the treatment. So remember, in any experiment, this is really what I want to talk about here more than this question. An experiment has 3 main parts: randomization, replication, and control. Okay, so we always start off by working with control. We want to control all the factors that we can. And so this scenario, we're selling records, so we want to try to control as many things that we can. You know, it might be location in the store, etc., 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 those sorts of things. The second thing that we want to talk about is replication. Replication just says, hey, we need to try to do this a lot of times. So they chose 70 stores and they randomly assigned 35 of them. Well, why does choosing a lot of things, why is that good? Well, the purpose of that is there's going to be differences in every single store. But by doing it to a lot of stores, then the differences between those stores will have the ability to balance out through randomization. So replication, it says do it to a lot of stuff so that the differences in the outcome is due to the treatment, not chance variation in the experimental units. So randomization, remember, balances out all uncontrolled factors. It doesn't eliminate them. They're still there, they're just in both groups equally. Okay, and that's important to remember. So then our best answer is D. It's reasonable to conclude that the difference was caused by the different cover designs because they were randomly assigned to the stores. So again, we see how important randomization is there. Okay. All right. Any questions so far? We made it through 10, going 20 minutes strong. Any ones that anything I can answer for anybody so far? Can people out there still hear me? Okay, got one response. 2. All right. So I'm hoping more people are out there. I guess we'll see. But if not, I'm glad you guys are there, and hopefully you're getting some help out of this. And if not, just please feel free to type in there. I've got that so I can monitor it. Okay. All right, number 11. Now, we've seen this one before. This one's a little bit tough. Basically, what I want to talk about is the difference here between what we have between a randomized design, a block design, and a matched pairs design. Okay, so that's what I want to just talk about first. So remember, completely randomized design. We take all of our experimental units. Okay, so we take all of our experimental units. I'm going to abbreviate EU for experimental units. Remember, that's the smallest unit that we apply treatment to. And we simply randomly assign them to 2 groups. And if we want to get really picky here, I'll do it because I'm on the internet, and this will be up for a while. I will then assign them to like group 1 and group 2. And then what I'll do from there is then I'm going to use some kind of coin, and I'm going to flip a coin to then figure out which group gets which one. So we'll have these guys get treatment 1, and these guys get T2, and then we'll come back and we'll compare something, whatever our response variable is. Okay, we'll compare those. So that's completely randomized design. Remember, there's nothing else really that's there. It's just completely randomized design. The next one that we can do is a block design. Now, block design is really good. It's a form of control. And what we do first is we start off with all of our experimental units, but this time we don't use randomization to start off. We first create blocks. So there's no randomization. And remember, we block on the variable that most closely associates with the response. And I'm going to write that down. Because if you're ever asked why you blocked or what you blocked on, you just make up and say, I blocked on this because this variable most closely associates with the response. Okay, so let's say we're talking about smoking, right? Or cholesterol. We know that smoking affects cholesterol. So what I'm going to do is I'm going to break everybody up into the smokers and the non-smokers. So we'll create, and I'm going to use that example here just to make life easy. So it always wouldn't be smokers, but this will just make it easier if you're looking back. So now that I've created these blocks, right, I can now randomly assign the treatments within the blocks. And the whole point is I want everybody that's in the treatment groups, in both treatment groups, to be the same as possible. So this guarantees that they will all be the same. Well, replication and randomization tie together. Okay, so now we'd have treatment 1 and treatment 2. So I'd have half the people up here and half here. And then I would do the same thing down here. Treatment 1 and treatment 2. So now if you look, I've got a group of people that are smokers in treatment 1, and I'm going to compare them to the group of smokers that are in treatment 2, so that they're the same based off of smoking. So their only differences should be due to their variability, or it should be due to the treatment. Okay, and same thing. Now I'm going to compare non-smokers, and then we'll come back and really, so we compare both here, and whatever our response variable is. And this way I'm comparing these people as closely as possible. All these people are similar to these people based off of smoking. And a very special type of blocking would be matched pairs. Okay, so it would be matched pairs. So matched pairs, we would actually group like patient 1 and patient 5 together, and they're the same on multiple things. And then we might flip a coin, and the older person gets the drug. New tails, they get the old, and the other person gets the other treatment. All right, I think matched pairs is easiest to just write out personally, but that's the idea. So we create these special blocks, and the blocks match the number like person 2 and 4 and 3 and 6. And the whole idea then that this person and this person are so similar, this person are so similar, this person are so similar, that the only difference is the treatment, and we've eliminated all those variables. Okay, so that was kind of a long story there, but let's go back now and look at this problem. And we see that we are now have a swimming pool, and they have 2 laundry detergents, detergent A and detergent B. Would you guys all agree with me? Those are the treatments. We never block on the treatments. Remember, we blocked on a variable that affects the response, not on the explanatory variable itself. So as the detergent towel comes in, it's placed into the only washing machine on the premise. When the washing machine contains 20 towels, the manager flips a coin to decide whether A or B will be used for that load. The cleanliness of the towels is rated, blah, blah, blah. So a completely randomized design kind of fits here. Even though this sounds weird, they get put in, and then they flip a coin. So they have a random chance to be either detergent A or detergent B. But let's look at why the other ones are wrong. A randomized block design with A and B as the blocks. Again, A and B are the treatments. They're the explanatory variables. They can't be the blocks. That's not possible. Okay? Because, remember, we create the blocks and then randomly assign from there. So that doesn't make sense to put all treatment A together and then randomly assign half and half. What would you assign to? Randomized block design with the washing machine as the block. Well, what did they tell you? As the dirty towels, they're placed in the only washing machine. There's only one washing machine. Again, that can't be the block. A matched pairs design, where were they paired? There was never a pair there. And an observational study. That's a great question here. Remember the difference between an experiment and an observational study is an experiment we impose a treatment. And that's what we did here. We flipped the coin. We imposed it. We didn't by chance wash them with that detergent and then analyze. So our best answer of all of them is letter A, which that is a tough one. But if you know your ideas behind what blocking is actually used for, then it makes a little sense. Okay, moving on. Number 12. So in the design of a survey, which of the following can help to minimize response bias? And I just want to talk about this one briefly. Response bias is in how the person responds. They lie, or they're not truthful, or they didn't understand with what they were doing there. Okay, so they didn't understand how to read the question, or the wording of the question was off. So we can reduce response bias by carefully wording the questions. Okay, the other type of biases that we can have non-response bias. This is where the persons choose not to respond. And we can improve that by, asking, not asking more people that it doesn't work, but having a follow-up question or something like that. Other biases might come in with how the sample is selected. Okay, but again, that's not going to be a response bias. That'd be our selection. Decreased sample size is never good. Increasing is always better. But again, that won't change response bias. You would just have more of the response bias just based off of the bigger sample. So that's pretty much that. All right, 13. For a sample of 42 rabbits. Whoa, n is 42, right? I don't care what you see. If we see we have a random sample of these things, we gotta circle that. So we know n is 42. The mean weight is 5 pounds, and the standard deviation is 3 pounds. So for a sample, so this would be my x bar, because that's the mean of the sample, and this would be sx, because that's the standard deviation from the sample. Now just remember, these two values are statistics, because they are values calculated from a sample. What would we like to know? Well, we'd really like to know mu, and we'd really like to know sigma, which would be the parameters. But all we have is our rabbits. We don't have all the rabbits. Remember, that's the only way to get parameters. So which of the following is the most likely true about the weights for the rabbits in this sample? So the distribution of weights is approximately normal because the sample size is 42, and therefore the central limit theorem applies. Now that one is not going to be correct. You might say, wait a second, 42 is bigger than whatever value you use for central limit theorem. We used 25 in my class. So what does that mean? That means the shape of the sampling distribution of x bars is approximately normal. What did A say? A said that it was the shape of the distribution of the weights were approximately normal. That's the individual x values. We're talking about x bars. So that's the difference between those two. So we don't know about this, but central limit theorem says that these x bars are approximately normal, not the x values. So important to understand. Okay, B, the distribution of weights is approximately normal because the standard deviation is less than the mean. I have never heard that ever, and I don't think you have either. C, the distribution of weights is skewed right because the least possible weight is within 2 standard deviations of the mean. Oh, let's think about that. So the mean is 5, the standard deviation is 3, so 2 standard deviations away would be -1, right? If you think about that. So here's 5, 2 standard deviations away would be -1, and we can't have any rabbits that weigh -1. So I do think that this is going to be a good one. Remember, to be approximately normal. So what that means is we have like a lower fence down here, and I think we would kind of see that the bunny's going to go that way. The distribution is skewed to the left because the least possible weights is within 2. Nope, so I think that lower fence is going to make it more values there and less values as you get heavier. And it has a median that is greater than the mean. I don't think we can answer that one. But remember, when our median is greater than the mean, that says we have a skewed left distribution. Which, if you understand that, that's basically the same thing that D says, so you could knock both of those out from that. Okay, moving on. 14, I'm going to skip. 14 was omitted, so don't even worry about that one. 15 is letter B. Again, I'm going to skip that. Just don't think it's worth our time right now, so we'll move on. 16. All right, I just wanted to set this one up, not that we're necessarily going to go all the way through it. So a complex electronic device contains 3 components. So as soon as I see that, and I see these probabilities of failure, if any one component fails, the device will fail. If the components fail independently of one another, remember, independent says the probability of A and B is A times B. Let's just do that, right? Or A given B is equal to just A. Okay. So what's probability that the device will not fail in 1 year? Okay, so here's what we want to do. If any one component fails, the device will fail. I wanted to look at this one. It's a probability question, but there are 3 events, A, B, and C. And A is going to be failure. So then A naught, or A complement, would be 0.99, which means that A doesn't fail. And B is 0.03, and B not failing is 0.97. Anyways, I want to do this one because we have 3 events independent. And the best way to set up anytime you have multiple events is with a tree diagram. So we have A could fail or A could not fail. So we got 0.01, 0.99. And independent, now we can set up event B. B could fail or B could not fail. And again, that would be 0.03, 0.97. And same thing down here. B, B not, and B 0.03, 0.97. And again, now we have event C, C not. It's kind of confusing. C, C complement, not C not, sorry. C, C complement, C, C complement. Okay? And again, we can fill in these probabilities, which were 0.04 and 0.96. So our question was, what's the probability that the device will not fail? So we need all 3 of these things to not fail, right? A can't fail, B can't fail, C can't fail. And remember, what do you always do with a tree diagram? Multiply those probabilities. So we do the probability of A times the probability of B times the probability of C. And we do all those together, and we come up with letter D. And there you go. So the strategy here, probability question, tree diagram. Okay, so tree diagram. Okay. Take a look at our next one. A large sample, 98% confidence interval. Again, that's just giving us a couple things. So 98% confidence for the proportion, all right, that are canceled on the intended day is 0.048 to 0.112. Now, let's quickly just remember our formula for confidence interval for proportions. P hat plus or minus Z star times square root of P hat, 1 minus P hat divided by N. Remember, this is my margin of error. This is my estimate, okay? What is the point estimate for the proportion of hotel reservations that are canceled on the intended day from which this interval was constructed? This is just a trick question, because if you understand what this says, hey, take p hat and go out some margin of error and subtract some margin of error, and that's going to give you your interval. But if you get this, you're going out the same distance to the left and the same distance to the right. So guess what that means? P hat is always in the middle of your confidence interval. So all I have to do is find what value is in the middle of these two. So I'm finding the average. Or guys, you could just plug in values to find out which one falls right in the middle. But 0.048 plus 0.112 divided by 2, that's going to give us our average. And divide by 2, and it's 0.08. So there you go. So remember, your point estimate is always in the middle of that confidence interval. All right, moving along. Okay, 18. Okay, so 18, a one sample T procedure to construct a confidence interval. So this is a one sample T interval. Let's just remember our formula. X bar plus or minus T star, S over the square root of N. Now remember, we use T, right, when we replace sigma with S. When we don't know sigma, replace it with S. There's extra variability. The extra variability requires us to use T star. T star makes the confidence intervals wider. Okay, and so then the answer to this one, which is our condition that we have here, and the answer is going to be letter D. So the reason that we need the population size to be bigger than 10 times the sample size, that is a question of independence. Sample size is large enough, that gives us normality. Central limit theorem is applicable for a sample mean, again, normality. So that's shape. Standard deviation is a good approximation of this population standard deviation. That one is not what it's going to be. If that was true, then we wouldn't need to use T star, we would use Z. The degree of dependence is negligible. That's independence, that's exactly right. See how dependence is negligible? So they're independent. And E, the sampling method is unbiased. That means that's from having a random sample. So those are just all the little conditions. I know I said those pretty quick. Okay, 19. Take a look at this one. This is, again, if we read the question, I know I'm going fast, guys. You could go back through and watch this. But a total of 1,000 tickets were sold. Okay, again, for $1 each. After all the tickets are sold, one ticket will be selected at random, and its owner will receive $50. The expected value for the net gain of the ticket is negative 0.95. So what's the meaning of the expected value? Well, first of all, this is the worst raffle ticket I've ever heard of. Only one person wins. Let's just quickly set up the probability distribution. So, I mean, this really stinks. You either win $50 or you win nothing. All right, and the probability that you win $50 is 1 out of 1,000, and the probability you win $0 is 999 out of 1,000. So we could find the expected value by doing our formula: this times this plus this times this. Okay, so we could do that, but they gave it to us. So what is expected value? Again, remember, expected value is the same thing as the mean, and it's the long run probability. So in the interest of time, that's going to be letter B. The ticket owners will lose an average of 95 cents per raffle ticket purchased. That's it. Remember, it's always talking about long run. Okay, so it's always talking about long run. Number 20. Suppose that on a hypothesis test for a single population mean, the HA says mu is less than 10. Assume that the HA is true for a fixed sample size and significance level. Alpha, the power of the test will be the greatest for the actual mean in which of the following? Power. Remember, power is the probability that we correctly reject HO. Three ways to increase power. Remember, increase alpha, makes it easier to reject. Increase sample size, okay? That makes it easier to detect a difference. And increase the HA, the distance of the HA. So, we look, it says mu must be less than 10. We got to find the one that has the furthest HA in the correct direction, right? So it's got to be in the correct direction. Since it was less than, we want to pick the one that's furthest on the low end, which would be letter A. So that's it. So power correctly rejecting. Make sure you go back and check out your type 1 error. Is when we reject a true HO. Remember, that probability is always equal to your alpha level. And then type 2 is when we fail to reject the HO. Fail to reject the false HO. Okay, and remember, these two, power and type 2, always add to give 1. Okay, all right, moving on. All right, 21. This question talks about residual plots. This is a big one, but remember, with residual plots, remember, a residual is the distance from our y to y hat, y minus y hat. Okay, how far is each point away from the line? So we have a linear regression. We have our point. How far this point is away from there is the residual. Okay, and remember, for a linear model to be a good fit, we need no pattern in the residuals. So we look at these and which one has no pattern, and the answer is letter C. Clearly a pattern here. What that says is your points would be like this. This would be above, 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 around it, and then below, 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 and then above, above, above. So we see kind of look like that. Okay. This one's scattered. This one, see how it's getting like this? Okay, that means the model's getting better as it goes along, but that's not good in the beginning. And this one's trumpeting, right? We see how those values are falling apart. Letter E is trumpeting. Okay, moving on. 22. Here we go. A random sample of 50 students. So N is 50. Again, we're trying to keep looking for these. 95% confidence interval for the mean. Okay, so we're talking about T star, right, people? X bar plus or minus T star, S over the square root of N, because it was one sample. So this would be a one sample T interval. And here's our interval, 6.73 to 7.67. So which of the following best summarizes the meaning of confidence interval? Yes, confidence interval. Remember, we just kind of have our generic statements. So our best answer to this one is going to be letter B. About 95% of all random samples of 50 students would result in a 95% confidence interval that covered the population mean number of hours. So remember, confidence is our long run chance that we're going to capture the confidence, the true parameter. Remember, it's never talking about this one interval. So if you look at all these other ones, 95% of all random samples would result in a confidence interval. This one, no, it's not about this interval. It's about all possible intervals. 95% of the students, no, we're talking about X bars, so we're not talking about that. 95% of students in high school, no, we're not talking about those students. A student selected at random from this population sleeps, no, what does that even talk about? That doesn't make any sense to you. So we can see those other ones don't make sense. So remember, confidence is 95% of all possible samples will succeed in capturing the parameter. Not ever about this one. Okay. 23 we're going to skip, but the answer to that one is letter A. That's just going to take us too long to do. Hopefully you guys are still hanging in there all right. Okay, 24. So taking a look at this one, here we go. So a random sample of 432, so that's n, revealed that 100 are in favor. So I have one sample, 95% confidence interval, talking about proportions, so p hat plus or minus z star, square root of p hat, 1 minus p hat all over n. If I know my formula, I'm easy peasy. So I need my p hat, which is 100 out of 432, which is 0.231. And so it'd be 0.231 plus or minus. Now it's 95%, so we know that's 1.96. Remember, proportions never deal with t, only means. It'll be 0.231 times 0.769, and we're going to take that whole thing and divide by 432. So that's it, which is letter D. And again, I mean, look at A, B, and C make no sense at all. And then D is just the difference between 90% and 95. I mean, you really didn't even have to do much with this one. 25, again, we're going to skip 25, but the answer is letter A. It's just a z-score problem. They told you that's normally distributed. So you're just going to do that one. So I think you guys can all work on that one, okay. 26. Okay. So a survey on the internet usage found that 79% of adults aged 18 or older use the internet. A broadband company believes the percent is now greater and will conduct a survey. The company wants to construct a 98% confidence interval to estimate the current percent and wants the margin of error to be no more than 2.5%. Assuming that at least 79% of adults use the internet, which of the following? So we're assuming that this is true. So they're basically telling us to use that as our value of pi, is what they basically say. Which the following could be used to find the sample size needed. So basically when they told us that, they told us not to use 0.5. So we need 98% confidence, which is 2.326. That's right at the bottom of your t distribution chart. So you got your t chart right at the bottom. You've got 98% confidence, 2.326. So we're stuck between C, D, and E. C would be under the assumption that we don't know what pi is, so that's out. And then so our best one is going to be letter D, because we're trying to estimate within 0.025. So 26 is going to be letter D. I'm not sure what they're doing for E. All right, 27, I really wanted to look at this one. So a manufacturer wants to compare brand A battery to brand B. So our HO would be that mu A equals mu B. Or we could do mu A minus mu B is 0. Our HA would be mu A lasts longer is greater than mu B. Okay? Here's the deal. I wrote that already, and I shouldn't have. But the question is this a two-sample t-test or a paired t-test? We know it's not z because we don't know sigma. So sigma 1 and sigma 2. So these are out, right? Z, you have to know sigma. Is it one-sided or two-sided? Well, we said it's greater, so it's one-sided. So C is out. So is it a paired t-test or a two-sample t-test? Now remember, paired goes like this. T equals x bar d minus mu d s over the square root of n. Okay? I need the mean difference, which would say we subtract all these. So that would mean that these two batteries would have to be connected, and these two batteries are connected. Is that the scenario here? No. This is a random sample of batteries. We have a separate random sample of batteries. They're not connected in any way. Therefore, we would not analyze mu d. We would analyze mu a and mu b. So this is a one-sided two-sample t-test. Now remember, it's one-sided because it's just greater than. So we just look at the HA. The only way to have it not be one-sided is where the HA is mu A does not equal mu B. So that'd be two-sided. Okay, moving on. 28. So this one, they give us a two-tailed, let's see. So the two-tailed test gave us a p-value of 0.44. Now remember, two tails means that you have two sides, and both those probabilities add up together to be 0.44. We want to switch it to a one-tailed test. So what do we know? The p-values could be between. Now this is the hard part because this always finds the extreme. So it could either be 0.22, which would be one-sided, or if it was a less than, it could technically be the other one, 0.78. So the possible p-values could be 0.22 or 0.78. So where did I get 0.22 from? That's half of 0.44. Okay, so that would be one side. That would be if it was this value and they were finding greater than. If they were doing that value and found less than, then it could be 0.78. So we got two different ways that one could go. All right, 29. I ran this one really fast. We have 33 tomato plants, 16 with A, 17 with B. What do you notice about the sample sizes? They're different. So this tells you it's a two-sample t-test. The tomatoes weren't connected at all. Okay. So what we want to do now is run the test in the calculator, which I already did. So you know how to run two-sample t-test, hopefully. Then you stat test two-sample t. The one trick is that we always say no to pooled. Okay. Gives you a t-test statistic of -2.55, a p-value of 0.016. So therefore, our only conclusion would be letter D. There's evidence of a statistically significant evidence because 0.016 is so small. All right, 30. Again, I know I'm starting to hustle here, guys. I want to try to get through this as quickly as possible. We've got about 7 minutes left. So let's look at this data. They took a random sample of 275 of people, and they classified them according to car, truck, red, black, white, or tan. What do you notice about this data? It's categorical. How many categories do you have? Color and types. You have two categorical variables. This is screaming chi-squared. Two sample, match pairs. Those are all quantitative data. This is not possible. When we have two categorical, we're talking chi-squared. So then which one is it? Is it independence or goodness of fit? Remember, goodness of fit is one variable with like red, green, yellow, blue, right? One variable with, colors of Skittles, right? Look, this is two variables with different categories they can fall. So this is chi-squared test of independence. How do we know it's independence and not homogeneity? It was one random sample. Remember, homogeneity would be a stratified sample. So that's our trick there. And they didn't even try to throw us off by throwing out independence. Okay, 31. This one's it's going to take us too long to kind of talk about this one, but real fast, they give you the p-value. And what you want to understand is no matter whenever you do a test, the p-value, okay, relative to alpha, so we know if the p-value is less than alpha, we reject. The thing is, guys, is even if your null is true, you would get a p-value less than the alpha, whatever that probability is or that area is. So if the p-values will be greater than 0.05, 95% of the time, because they're saying that there's no relationship, right? So they say that. So that will happen. 5% of the time you get p-value less than 0.05. Then about 95% of the time it will be greater than that if there was no difference. 2, there will be equal number of experiments showing positive and negative values. Again, they're saying that there's no effect, so it would be centered at 0, and the mean would be at 0. So half would be above and half would be below. So that's correct. And now and 3, when 95% confidence intervals, those confidence intervals will include 0 95% of the time and be about 95, right? Why does it include 0? Because there's no effect. So it's 1, 2, and 3. I know I'm starting to go fast. We're just in the last 5 minutes. Okay, 32, 95% confidence interval for slope. Remember how this works out. Our special boot here. This is my slope. This is the standard error of the slope. Okay, this is my t-test statistic under the HO that beta is 0, and this is the p-value under the HA that beta does not equal 0. Okay, so just remember that. S is the standard deviation of the residuals, and there's R squared. So a 95% confidence interval. Well, they made all the t stars the same, so I don't even care. Remember, degrees of freedom is n minus 2. So it's it's x bar. No, it's not. It's a little b plus or minus t star times the standard error of the slope. This one's easiest. So it's 2.697 plus or minus 2.228. They gave us that. And then times the standard error, which was 0.745. And the one, assuming that the conditions, which the following give us the margin of error. So remember, our margin of error is just this chunk right here. So 2.28 times 0.745. Okay. All right, last 3 minutes. 33 is 2. Is letter C. I'm going to skip that one. Okay, 34. So in 34, they tell us that the probability that it will stop working in 2 years is 0.05. The probability that a new oven is damaged and stops working is 0.04. And the probability that an oven is damaged during delivery is 0.1. Given that the new microwave is damaged during delivery, what's the probability that it stops working? There you go. So that's the question. So now we go right to our formula sheet and we write this out. Probability that it stops working and damaged divided by the probability that it was damaged. Guys, it doesn't get easier than this. You just write out the formula. Where did I get this from? My formula sheet. Stops working and damaged, 0.04. Divided by damage, 0.1. That gives you 0.40. So just look at your formula sheet and go back. Jake just asked for the answers. If you just Google the questions, the answers will pop right up. So you can Google answers to 2012, but I can post it on the classroom tomorrow, no problem. Okay, 35. We're doing great, guys. We're going to get right through this. So they tell us that 24.5 is the value. Drinking water is considered safe when the average level is 24.5 or less. A RAM sample of 28 area produces a mean perchlorate measure of 25.3, which is the appropriate alternative. What would we try to prove? We would try to prove that this value is greater than 24.5. So the HA would be that mu is greater than 24.5. And why not 25.3? Because that's my X bar, right? Remember, we always talk about the parameters here in these, okay? So we always talk about the parameters. All right. 36 is going to be, again, I'm running a little low on time. The following statements is the correct value of 19. 19 is the slope. Okay, so don't forget that's your slope. Okay, that's the little b. And that says that we know for every 1 unit of the x, on average, how much the y's will change. And that's going to be letter B. On average, there is a predicted increase of 19 for every 1 increase of the lead. All right, and I'll let you guys read that later. Again, I want to make sure that I get you out on time. 37. Okay. Random samples of size 100. Which the following describes as sampling distribution? Yes. So the mean of the x bars. What do we know? Mean of x bars is always equal to mu 206,274. Standard deviation of the x bars. We know is always equal to what? Population standard deviation over square root of n. Where do I get these rules from? My formula sheet. And again, we see sample means. We know that it's yelling at us to do x bars. So the square root of 100, and that would just divide it by 10. So I know that I'm down to this one. And then the last class question is what happens to shape? Well, 100 is greater than 25, so approximately normal by CLT. What's approximately normal? The x bars. So letter A. Okay, and again, I know I'm hustling. I want to get you guys out of here. 38. I'm just going to let you guys take a look at this answer. The answer is letter B. This is what your null hypothesis would be, that they're the same. Again, remember our HOs, we always assume they're the same. 39. This one is just like graphing 2 dice. Again, this is just going to be letter C. I can answer any questions on that. And then number 40. The probability of winning a game is 0.5. If at least 70% of games are won, the player will win the prize. Well, what would it be easiest to do? To win 70% with a smaller number of trials or more trials? Remember, the law of large numbers says the probability will approach that value with more trials. So we want it to be smaller. So answer would be letter A. Now you could do binomial. If at least 70 CDF, and so you could use n is 10, p is 0.5, but you have to change the counts. So 70% of 10 would be 7 to 10. So you could do that there. You could do it for 20, p is 0.5, and 14 to 20. When you could try it for 100, oops, 0.5, and that would be 70 to 100. Try them all out, and you'd see which one is the largest probability. It'd be letter A. Well, guys, thanks so much. It's 9:01. I hope this was helpful. If you want to stay for a second, I can answer any questions, but like I said, I really hope this helped you guys out. So thanks so much for coming, and we'll see you guys this week.